Today we will talk about zeros of polynomial functions. We will continue to use synthetic division to discover things we can learn about a polynomial function by using that tool. So the first thing that we will talk about is the factor theorem. Now remember that we discussed if we do synthetic division and we end up with 0 in the remainder spot, that told us that value would be a 0. In other words, x minus that value, whatever our k was that we were dividing, would actually be a factor of the polynomial. So we're just going to look at the same concept with a little different form for the question today. And it says for any polynomial function f of x, x minus k is a factor of the polynomial if and only if f of k equals 0. In other words, if we try to divide the k value into the polynomial using synthetic division and we get a 0 in the remainder spot, then we know that that is actually a factor. So let's take this first example. If we need to determine whether this is a factor or not, let me make sure you can read the function clearly. You may have a little bit of an issue with the way some of the signs transferred in. This says that f of x equals 3x to the fourth minus 48x squared plus 8x plus 32. Now, if I'm going to use synthetic division, remember that I need to make sure that my polynomial is ordered in descending order and that I put any missing terms, I put in a coefficient value of 0. So if I write out my row of polynomial coefficients, my first one will be 3. That goes with the x to the fourth. I do not have an x to the third term, therefore I will need to put a 0. X squared has a coefficient of negative 48. The x term has a coefficient of positive 8. And my constant term is a positive 32. My k value I need to identify carefully. If I'm determining whether x plus 4 is a factor of the polynomial, k would have to have a value of negative 4. Remember, when it follows the x, we're actually using the opposite sign of what we see. So we are ready now to divide. Where negative 4 is our divisor, we'll use synthetic division with these polynomial coefficients. So bring down your first coefficient of 3. If I multiply 3 times negative 4, I get negative 12. When I add that second column, obviously I get negative 12. Now, the value that goes under negative 48 is a negative 4 times a negative 12, which is a positive 48, and that actually zeroes out. But we're not done. We have to get all the way to the end of the row. So now I will have to multiply 0 times negative 4, which is 0, add that to my next coefficient, which is 8, and that gives me 8. And in my final spot, 8 times negative 4 is negative 32, and we did end up with a 0 in the remainder spot, therefore it is a factor, simply because our remainder is 0. Now, the next one, we're still testing to see if x plus 4 is a factor of the polynomial. That means we are still using a k value of negative 4. If I go through this polynomial function to get my coefficients, again, if you have any issues seeing signs, I'll call them out to you. We have x to the fifth for the first term. These are in descending order. So my coefficient is 1. I do have an x to the fourth term. It is a positive 6x to the fourth. So 6 is the next coefficient. I do have an x to the third term. The coefficient is positive 11. So that goes in the next spot. My x squared term has a coefficient of positive 12. My x term has a coefficient of positive 5, and my constant is negative 20. Okay, no missing terms in this one. We are ready to use synthetic division. Bring down that first term, I get a 1. 1 times negative 4 is a negative 4. When I add that to 6, I get a positive 2. Now we multiply negative 4 times 2, we get negative 8. We add the next column, and 11 minus 8 is positive 3. 3 times negative 4 is a negative 12. Here we have another instance of getting a 0 in the midst of our problem, but we're not at the end. We have to keep going. So negative 4 times 0 is 0. When I add 5 and 0, I get 5. Now 5 times negative 4 is negative 20. Be very careful here, because when I add, I don't get 0, I get what? Negative 40. So what does that tell me? Not a factor. I have to get 0 in that remainder spot in order for this to be a factor. Okay, now we will test to see if we can factor a polynomial completely, provided we have been given one of the zeros. So in other words, we'll start with synthetic division, and then we will see if we can get it down to something that would be quadratic in nature, because we do know how to factor quadratic equations. So that means if you're going to do this, you would either have to have more than one zero given to you to work with a polynomial that's greater than a lead term of being x to the third. Otherwise, I'm going to give you a function where the largest exponent is 3. It's going to be something x to the third for your first term. And after you use the 0 I give you, you should be able to factor the rest of it using any of the factoring skills we learned back in Chapter 1. So, if I tell you that 5 is a 0 of this function, that means we will not change the sign. We're using 5 because it is the 0, and we need to use synthetic division by pulling out our row of coefficients. So the first term is 6x to the third, so I'm going to need a 6 in the first spot. The next term is negative 37x squared, so we need a negative 37. My x term has a coefficient of positive 32, and my constant is a positive 15. Now, when I bring down that first term, 6, and I multiply 5 times 6, I get 30, which goes under the negative 37. Adding those together will give me negative 7. 5 times negative 7 is a negative 35, so that goes under 32. Now when I add that column, I will have negative 3. And 5 times negative 3 is negative 15, and sure enough, I get 0 in that remainder spot. That's a good thing. They told me 5 was a factor. That means I should get 0 in that remainder spot. But notice what I have left. I can take the row of coefficients for my quotient, and I can put those variables back in. And that would mean I'd have 6x squared minus 7x minus 3 that I now need to factor. So whatever method you want to use, if you would like to use the AC method, you may certainly do that. If you simply want to open parentheses, do a little guessing and checking to get it factored, whatever method you prefer. I'm going to speed things along because I'm going to assume you know how to factor, and you should end up with 3x plus 1 in one of your parentheses, 2x minus 3 in the other parentheses. Now, if I used FOIL or the box, I could multiply these back together and I could double check to see that it really will give me 6x squared minus 7x minus 3. It does. But be careful, you haven't fully answered this question yet. It tells you to factor that original polynomial into linear factors if 5 is a 0. So what I did is I took this remainder well, not the remainder, the quotient, sorry, coefficients, and I factored that, which is what the 3x plus 1 times 2x minus 3 is, but don't forget, we have another factor we need to put with it because we were told 5 is a 0. That means when it goes back into parentheses after the x, it will be x minus 5. And it takes all three of those parentheses to fully factor the original polynomial. So make sure you read your instructions carefully and you work all the way to the end before you stop. Now the next section talks about the rational zeros theorem. The rational zeros theorem is an important theorem. However, I do believe it's something that is a little bit archaic. I don't think most people will choose to use this method in order to factor polynomials because it is not nearly as efficient as using some other things. Sort of for the same reason that you probably don't go see a local blacksmith on a regular basis. You don't tie up your horse when you come to class. You come in a car because that's a more efficient way to travel. But I do want to explain how the rational zeros theorem works. There are some college algebra instructors that think it's very important that you know how to use this and can use it properly. I will not have a test like a question like this on the test. Instead, I will give you a question similar to the one we just did, where I will give you a 0 to get you started, or I will give you a graph, and you can see from the graph one of the zeros to help get you started on synthetic division. This is a tool you use when nobody has told you what any 0 is, and you're going to have to figure out the possibilities. So let me explain this quickly. It says if P divided by Q is a rational number written in lowest terms, and if P over Q is a 0 of F, so in other words, some rational number, it doesn't have to be a fraction, it's just that it can be written as a fraction, then a polynomial function with integer coefficients is what the function is. P is a factor of the constant term, and we'll put that in this first blank, of the constant term, and Q is a factor of the leading coefficient. Okay, so what this does is instead of having to just randomly guess numbers to see if we try synthetic division, will it actually divide out and be something workable? Instead, we're going to narrow down our options and have a smaller number of possible zeros we can test. But using this method, you just have to kind of guess and check. You randomly pick something and you try it to see if it's going to be a 0. So let me explain how this would work for this particular function. We have 8x to the fourth minus 26x to the third minus 27x squared plus 11x plus 4. Now, that particular function means that our p-value is going to be the positive 4. Our q value will be the positive 8. Okay, so what we have to do is come up with a list of the factors of 4. Now, when I say factors of 4, I mean tell me every possible number that could possibly divide into 4 evenly. And keep in mind, we're going to have both positive and negatives. So we really double up all the possibilities here. So I know 1 will go into 4. That means I can have a positive and or a negative 1. 2 will go into 4. So I'm going to have a positive or a negative 2. 3 doesn't, but 4 does. So positive or negative 4. There are 6 different factors for 4. Now, the factors of 8 are very similar, except we're going to have to add an extra one. We still have the plus or minus 1, plus or minus 2, plus or minus 4, but what else should be in the list? Plus or minus 8. Okay. Now that those are listed, remember our only possible zeros for this function come from creating the fraction p divided by q. The problem is we have to put together every possible option we get when we try to do p divided by q. Think about this for a minute. It means that if I were to use 1 from my factors of 4 for a numerator, I could put it over 1, and that would give me a positive or a negative 1. If I were to put it over the next one, I could have a positive or a negative 1/2, 1 over 2. If I keep moving down the list, I can have a positive or a negative 1/4. And the last one would be a positive or a negative 1/8. Now that's when using 1 as a factor of 4. I have 2 other options here. I could also have a 2 or I could have a 4. Now if I use 2, that means I'd get a plus or minus 2 over 1, which is the whole number 2, but it's both positive and negative as options. Now when I move down my list, 2 over 2 reduces down to be the whole number 1, and I've already accounted for that in my list of possible factors using p divided by q, so I don't write it down again. If I keep moving down the list, 2 over 4 is 1/2. That's already in my list. 2 over 8 is 1/4, and that one's already in my list. So now let's move over to using 4 as a factor for our p-value, and that would mean I could have a plus or minus 4 over 1, which is just the whole number 4. You don't have to put it over 1 if you don't want to. We'll clean them up when we actually test them out anyway. And again, when I move down the rest of the list, 4 over 2 reduces down to be 2, which is in my list. 4 over 4 is 1, which is in my list, and 4 over 8 is 1/2, which is in my list. But look at our list now for possible zeros. We have 1, 2, 3, 4, 5, 6 different numbers listed, but they both have positive and negative signs. That's 12 different possible zeros, and the only way I know if any of them are going to be a 0 is by using synthetic division to see if I get a 0 in the remainder spot. Now, if you were doing this on your own, odds are pretty good you might want to choose whole numbers first to test out for synthetic division instead of actually using the fractions. You can use the fractions, but you may not want to. So here's where we'll start. I do see that I could either use a positive 1 or a negative 1. And so what I'm going to want to do is choose one of them to get started. So let's try a positive 1. Now remember, if 1 is a 0, it would mean x minus 1 is a factor. So let's put our row of coefficients down. We're going to have 8. We're going to have negative 26. We're going to have negative 27. The next thing is positive 11, and then we're going to have a positive 4. Okay. Bring down my 8. 8 times 11 is 88. When I add that together, I'm going to get, let's see, 8 minus 6 is 2, and 8 minus 2 is 6. That looks like a positive 62. Now, 1 times 62 is 62. I've got to add that to negative 27. When I do that, I'm going to have a 5 and then a 3, and that's going to be a positive 35. 1 times 35 is 35. And so when I add those together, 11 and 35 give me 46, and I can already tell 1 times 46 is 46. This is not going to be a 0 because that's 50 in my remainder spot. So trying to use positive 1 didn't work. Let's use negative 1. Got to repeat the same row of coefficients. Now, bring down the 8. 8 times negative 1 is a negative 8. So when I add negative 26 and negative 8, I get a negative 34. When I multiply that times negative 1, I get a positive 34. Add that to negative 27. That gives me 7. 7 times negative 1 is a negative 7. And 11 minus 7 is 4. And what do you know? Negative 1 times 4 is a negative 4. That will give me a 0. So here's what I know. A negative 1 is going to be a 0. That means x plus 1 is going to be a factor. So I'm going to come up here and I'm going to write f of x equals x plus 1 in parentheses, and I'm going to go look for more factors now. Since it's raised to the 4th power, I should get 4 different parentheses. Now, I can take what I have left. I don't have to go back to the original. I can use this row with the 8, the negative 34, the 7, and the 4, and I can test out something else. So what I think I'll do is I will go to the positive 4. By the way, if we were looking at a graph, if you had a graphing calculator, you would probably, and this is why this is not necessarily an efficient way to start, you would be looking at a graph and you would have a pretty good idea that this graph is crossing the x-axis at what looks like negative 1 and what looks like positive 4. And that would give you the clue about start with using those values for zeros until you get down to the things that might be fractions, and then you will find those by factoring. So let's take 4, divide it into this row of coefficients we have left, and so I bring down the 8. 8 times 4 is 32. When I add that to negative 34, I get negative 2. 4 times negative 2 is negative 8. Add that to 7, I have a negative 1. 4 times negative 1 is negative 4, and looky here. We have a 0 in the remainder spot. What that tells me is that x minus 4 is also a factor. Now to get the other 2 factors, I will squeeze in my variables, 8x squared minus 2x minus 1, and that I will factor using whichever method you want. You can either open the parentheses and guess and check, or you can use the AC method, but it should end up giving me 4x plus 1 and 2x minus 1. And again, you can use FOIL or the box to double check, and what that tells me is I now have all 4 parentheses, and this would be the completely factored form of the original polynomial. So the rational zeros theorem is helpful because without a graph or without knowing what a 0 is, it can narrow things down for you. But notice it only gives possible rational zeros. It won't tell you whether it's an actual 0 unless you plug it in and you check to see if you get a 0 in the remainder spot. Now, in the fundamental theorem of algebra, here's what we know. Every function defined by a polynomial of degree 1 or more has at least one complex 0. We're not, remember our complex numbers are the ones that have an I. They have a square root of negative 1 involved somewhere. We're not going to actually work with factoring those, but we could. So it's just to let you know that you will have complex zeros if you look for them. Now, the number of zeros theorem is also very helpful. Notice a moment ago I told you because our first term was x to the 4th, we should have 4 factors. Look at the number of zeros theorem. A function defined by a polynomial of degree n has at most n distinct zeros. Because my first term was x to the 4th, I knew I should get 4 parentheses. Now notice this says at most n distinct zeros. That's because I could have some parentheses that repeat. In other words, it might be a double root. It would be a 0 more than one time. It would have multiplicity. And so that's what we're going to talk about here, is what we can do if we are trying to work with a polynomial that has some multiplicity of zeros. And what we're going to do is kind of go the opposite direction on this. I'm going to tell you what the zeros are, and I'm going to give you one point that's on the graph, and from that you're going to be able to write the function, the equation that would go with this polynomial. So here's what we know. We are going to be using something called root form for a polynomial. Basically, it looks like this. Our function could be written in factored form. Remember when we have an a that is in front of our function, That simply tells us about stretches or shrinks. If it happens to be negative, it would tell us about reflections. And depending on how many different roots we have, again, root is another word for a zero, an x-intercept. In factored form, we would have x minus each of these x-intercepts. And so on this particular problem, they tell me I have three zeros, -3, -2, and 5. And I have this point that I know exists on the graph. F of -1 is equal to 6. So I'm going to use this root form, what it would look like in factored form. And you know what? If I knew there was no stretch or no shrink vertically, that would mean my A value is 1, and I'd be ready to plug in and I'd be done. The problem is I don't know that. There could be some value. So here's what we will do. We'll first plug in those root values. So our -3 will be our R1, our -2 is our R2, and our 5 is the R3. So I'm going to have, now remember our signs are changing because it's x minus the root. So that turns it into x plus 3. That'll turn it into x plus 2. And the x minus R3 becomes x minus 5. Okay, I still do not know what the A is. And I have x's and I have an f of x. That's why you need a point that's on the graph. Remember what it's telling you. It's telling you that when x is -1, your y value is 6. And guess what? We can go back to this function and we will substitute 6 for the f of x because we know the y value is equal to 6. And everywhere I have an x, I'm going to put in that x value of -1. Because I know that when x is -1 on the graph, the y value is 6. This is now going to leave A as the only unknown, and I will find out if I have a stretch or a shrink. So when I clean this up, I get A times -1 plus 3 is a positive 2. -1 plus 2 is a positive 1. And -1 minus 5 is a -6. Well, multiplying all of that together gives me a value of -12 times A. And to solve for A, I would divide each side by -12, and I get the fraction A equals -1/2 when that reduces down. I have all the information I need now to go back to this line. I will substitute in what I just found the value of A to be, which is -1/2. And I will rewrite this function now in this root form, x plus 3, x plus 2, x minus 5. Now, when we test or when we quiz, leaving this in root form is perfectly acceptable. I don't see any reason why you need to expand this out and write it in standard form. However, I will warn you, when you're working online, the computer will want your homework to be expanded out and written in standard form. Therefore, when you're working on that, if you have any difficulty expanding it, then you can show me your work and bring that to me, and I will go back and give you credit if you do have it in correct factored form. So bring that work to me if you want full credit. Now, the last example we have simply says that 4 is a 0 of multiplicity 3. Now remember, I told you sometimes we end up with zeros that occur more than once. In other words, the parentheses are going to match 3 times on this because we have 3 different parentheses where the 0 is going to be 4. Now, that means my R1, my R2, and my R3 are all 4. And the point that's on my graph is f of 2 equals -24. So here's where we start. We go to that root form. I'm just going to recopy it. And then we'll start plugging in. So what I know is that the r value, each of these roots, since it has multiplicity of 3, the root is 4. That means I have x minus 4 times x minus 4 times x minus 4. I have that in parentheses 3 times. The part I haven't used yet is this part over here. My x value is how much? 2. Remember, it occurs in the parentheses after the f. So I'm going to substitute 2 everywhere I had an x. What is the y value when x is 2? Well, according to this, it is negative 24. So if I clean this up, negative 24 is equal to, and I take 2 minus 4, which is negative 2, times negative 2, times negative 2, and that would give me a negative 8a. When I divide each side by negative 8, my a value is positive 3. Now I can take that, plug it back in to this line, since I now know what a is, and that means in factored form my function is equal to 3 times x minus 4, and if you'd like to use 3 as an exponent, you certainly may.